Okay, this is 2010, Form B, number 2, vector problem. We have an x velocity given here, the derivative of the x position and the derivative of the y position, so that's x velocity and y velocity. And we know that at time 0, when t equals 0, x is -2 and y is 3. Okay, so for times 0 to 1.5, find all values of t at which the line tangent to the path is vertical. Alright, well, tangent lines, when we're in parametric mode like this, we're looking for dy dt over dx dt be vertical. That means that's undefined, right? And that happens when dx dt is 0. So let's see if we can do that. Dx dt excuse me, is 14 times the cosine of x squared times the sine of e to the x. Right? Who makes these things up, huh? What kind of crazy function is that? Let me just make sure that I'm in radian mode. I am. We'll go ahead and go to the window. I'm interested only in times from 0 to 1.5, and I'm interested in where those are 0, so I don't really care what the y values are. I just want to see where it crosses. Oh, there's one. There's 2. Alright, so second calculate, looking for those zeros. Come on, little guy. There he is. So looking for that one. Oh, something bad happened. Sorry. Let's try that again. Second, looking for the zeros. Left bound. Right bound. So that happens at t equals 1.145. 1.145 and t equals 1.253. Okay, part B. Write an equation for the line tangent to the path of the particle at t equals 1. Okay, so to find that I need point and I need slope. So how do I find those points? Because I don't have equations for x and y, but I do know this, and I do have one for t equals 0. I have an x value and a y value. So if I want to know the x and y coordinates at t equals 1, I have to do a couple little fundamental theorem things here to find those points. I'm going to do, if I do the integral from 0 to 1 of x prime of t dt, that's equal to x of 1 minus x of 0, right? And I know that this is -2. So the x of 1 that I'm looking for, my x coordinate, is equal to this integral. That's minus -2, so that would be plus 2 here, and I'm subtracting it to the other side, so that would be minus 2. And then the integral from 0 to 1 of y prime of t dt, well, that would be y of 1 minus y of 0. So y of 1 is what I'm looking for. Y of 0 is, what is it, 3? 3? Minus 3. So my y coordinate is going to be that integral, which I'll do with my calculator in a minute, plus 3. Right? So let's get our calculator and do that. So I'm going to go ahead and put them both in here, anticipating what might come. So y1 is, oh poop, was it already in there? It was, wasn't it? Cosine of x squared sine of e to the x, right? And I want to find the area under that from 0 to 1. So yep, there it is again. Calculate the area under that from 0 to 1. You could do this on the home screen using fnint, of course, right? Maybe that's faster for you. Maybe you like that better. So I'm finding this right now. It is 11.315 minus 2. So that's 9.315. That's my x-coordinate. And then my y-coordinate, go back to y equals and put in, let's turn this one off for the moment. Oops, try that again. And put in the y derivative, which is 1 plus 2 sine of t squared, or x squared, plus 2 sine of x squared. And let's graph that one. We'll find the area from 0 to 1 under that. So now we're finding this. Oh, it's done. So second calculate. It's not on the screen, but it doesn't matter for what we're doing right now. Going from 0 to 1. That's 1.621 plus 3 is 4.621. Okay, so there's my x and y coordinates. And then to find the slope, I need to find dy dt over dx dt evaluated at time 1. So dy dt, let's see, if I go here, I can do value, that's y2, right? So that's the y2, that's on top, 2.683 over, go back to this and turn that one on and this one off. This is some tedious calculator work, but easy points if you're careful. And go ahead and graph that again, and then do second calculate that value at 1. That's 3.107. So the slope of my line is 2.683 over 3.107, which is about 0.864. So my line is y minus y is equal to m times x minus x. That was fun. I'm tired. Okay, now, part C. Find the speed of the particle at time 1. Well, here, I have a little bit of, we saved a little bit of time here, perhaps, because I have those, I can do a speed function like this. I can do the square root of y1 squared plus y2 squared. right? There's my speed function. So I can graph that. And then plug in 1. That'll give me the speed at time 1. .105. So that's the square root of dx dt squared plus dy dt squared evaluated at t equals 1, and that's 4.105. You've got to show this. D. Find the acceleration vector. Again, because I have those in here, I can make pretty short work of that. That's the derivative of y. That's y, sorry, x double prime of, where do they want it? At 1? At 1, comma, y double prime of 1. And these are x prime and y prime. So I just need to go back to my home screen, and I can do math 8 and deriv of y1 comma x comma at 1. That's negative 28.425 comma the same thing but at y2. All right. That was fun. Not.